Hello, my name is Aiden Rabzadeh, and this is the counting circuit. Here's my final soldered PCB. When I press the button, it starts counting, and I can switch this so the up/down pin is connected to ground, so it counts down. To the counting circuit comes from the pull-up resistor and button at the start of the NAND gate oscillator, which allows for low side switching. At rest, since this is in a pull-up resistor configuration, both inputs of the NAND gate are high, meaning that the output is low. This low signal is carried through to pin 1. Even though pin 2 does not have a higher low signal yet, according to the NAND truth table, as long as one of the inputs is low, the output will always be high. So this high goes through R4 and R3, feeds back into the NAND gate, and makes this high. Now it also goes into pins 5 and 6, making both these high, so pin 4 is low, and pins 11 and 12 are both low, so pin 10 is high, which means that the LED is off because it has no path to ground. The difference in charges between pin 3 and 4 also charges capacitor C2 before the button is pressed. When the button is pressed, the inputs of the first NAND gate have a direct path to ground, so they'll both become low, making the input high. Now, this capacitor charges instantly because there's no resistance, and some of the current trickles down into R2. This high signal carries on to pin 1, and now since there are two high signals, makes this low, 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 high, 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 and low. This makes the LED turn on because now it has a path to ground. After pin 3 is low, C2 discharges through R4. Once the capacitor's charge reaches below half of the supply voltage, pin 2 of the NAND IC reads the signal as low. This means that the output of pin 3 is now high, so now the LED turns off. When pin 3 of the NAND IC turns high, C2 begins to charge again. When C2 exceeds half of the supply voltage, its left lead is high, and this signal is carried through R3, so pin 3 is now low because both of the input pins are high. This cycle of discharging and recharging of C2 continues on, and that is how the oscillation happens. RC2 controls the frequency of the square wave. If I decrease the resistance, the frequency will increase, and if I decrease the capacitance, the frequency will also increase. RC1 controls the duration of the square wave. If the capacitance is increased, the duration becomes longer, and if the resistance is increased, the duration also becomes longer. This square wave is now sent to pin 14 of the 4017. Pin 15 reset and pin 13 disable need to be conditioned in order for this chip to function properly. If a pin needs to be conditioned, it should usually connect to ground or power, but different pins on different ICs have different requirements. In the circuit, the 4017 is only used to divide the clock signal outputted from the NAND gate oscillator by 10, because if the clock wasn't divided, the oscillation would be too fast, so the counting would be harder to observe. The clock signal from pin 12 of the 4017, which is the divide by 10 output, is inputted into pin 15 of the 4510 in the counting circuit. The 4510 counts each rising edge of the inputted clock signal and presents the count as a binary number on its output pins. It counts from 0 to 9, then resets. Up, down, reset, carry-in, and preset pins should all be conditioned for regular use. The up-down input determines the direction of the count. A high signal will make it count up, and a low signal will make it count down. In this circuit, I connected a LDR to the up-down pin. One side is connected to power, and the other side is connected to ground through a resistor. So if I cover the LDR, it will count down. When the reset pin is high, the count resets to 0, making all the outputs low. So for normal use, it should be connected to ground. Here I used a pull-down resistor so that when I press this PBNO, it will reset the count because it has a direct path to power. In my circuit, I linked two 4510s. To do this, all clock and reset inputs should be linked. Also, carry in on the first counter is low, and carry out feeds carry in of the next counter. The 4511 CMOS function IC takes the 4 binary coded decimal BCD outputs from the 4510, decodes them, and presents the count on its 7 output pins in 7-segment display formats. For example, when it receives 0011, it knows which output pins it should send high to display a 3 when connected to 7-segment display. This is because an arrangement of many logic ICs inside each of the output pins. The 7-segment cathode display takes the outputs of the 4511 into specific pins to display the count of the clock signal periods in decimal. The reason I have resistors connecting to the 7-segment display is because the 4511 and the 7-segment display both have no built-in resistance. This is my counting circuit. When I press the button, the counting begins. I can increase and decrease the frequency of the counting with this potentiometer. I can also reset by pressing this button and count down by covering the LDR with my hand. I also put a on-off switch, so every time you want to use it, you don't have to unplug and replug. Thank you so much for watching, and I really do hope you learned something.